Alright, so in past lectures we've seen how to differentiate a lot of functions. We know how to differentiate power functions, we know how to differentiate trig functions, and we know how to differentiate products and quotients and compositions of all these types of functions. But there's still some more functions we haven't seen how to differentiate, and the next ones that I'd like to look at are the exponential functions. So exponential functions are functions of the form f of x equals a to the power x for some constant a which is greater than 0. So let's suppose we want to find the derivative of this function. We don't know a rule for it, so let's just try to use the definition of derivative. So we have the derivative of a to the power x is equal to the limit as h approaches 0, a to the power x plus h minus a to the power x, all divided by h. So now we can apply some properties of exponents. So particularly if we have a to a sum of two powers, we can split it up as a product. So this is the same as the limit as h goes to 0, a to the x, a to the h, minus a to the x, divided by h. So that's just properties of exponents. Then we see that we have an a to the x in both these terms here. So we have a to the x times a to the h minus 1 divided by h. And so we want to take the limit of this thing as h goes to 0. A to the x does not depend on h, so we can pull it out front and get a to the x limit as h goes to 0, a to the h minus 1 over h. Now, unfortunately, this limit here is not one that's easy to compute. I'm just going to call it L for the moment. So L is some constant. We don't know what its value is at the moment. If we do that, we can write this as L a to the x. So notice the derivative of a to the x is equal to a constant times a to the x. So in other words, the derivative of a to the x is proportional to itself. So that's sort of really interesting. Usually when we take the derivative of the function, it ends up looking like a different kind of function. Like, for example, sine turned into cosine. If you had a power function, the power decreased by 1. But here the function remains almost the same. There's just a constant out front. So the question is, though, what is the value of this constant? Well, it's this limit, which I said we don't know how to compute. But we can estimate the value of this limit if you pick a value of a and then just plug in really small h values, use the table method for estimating limits, then you can try to figure out what L is for any fixed value of a. So it turns out if we pick L to be equal to Euler's number E, which is approximately equal to 2.71828, then 1828, well, whatever. 2.71 is probably sufficient for most cases. So if we pick, or sorry, not L, if we pick A to be this number, then we can plug in smaller and smaller h values, and you'll see that L actually ends up approaching 1. So this means if a is equal to e, we get the result that the derivative of e to the power x is equal to e to the power x. So this is what makes e such a special number in calculus. The derivative of e to the x is just equal to e to the x. We don't actually have to do anything to it. And in fact, c times e to the x, where c is some constant, are the only functions which are their own derivatives. This makes e to the x a very special function. It's the only function with this property where you can take its derivative and it remains unchanged. So that's really cool. And not only that, so I've told you the value of L now when a is equal to e, but we still don't know the derivative when a is a different number. But it turns out we can use this remarkable fact about e to the x to help us figure out the derivative of a to the power x when a is a different number. So let's see how to do that. So the derivative of a to the power x is going to be equal to, by properties of logs, the derivative of e to the log of a times x. So remember, e to the log of a would cancel out, and you'd just be left with a to the power x. So really I've just rewritten this function in an equivalent way. Now how do I take the derivative of this function? Since I know the derivative of e to the power x, and log of a is just a constant, this can be done by using the chain rule. So by the chain rule, the derivative of the function inside the exponent is just log of a, and then I have to multiply by the derivative of the outside function, which is e to the log of a times x. But now remember, I said a to the x is equal to e to the log of a times x, so I can simplify this. This is just equal to a to the x, so it simplifies to log of a times a to the power x. So now we know how to take the derivative of any exponential function. So just as an example, the derivative of 3 to the power x would be equal to, in this case a is equal to 3, so it's log of 3 times 3 to the power x. So now we know how to differentiate power functions. We can do a lot more interesting things. So for example, let's suppose I want to take the derivative of x squared times 2 to the x. Well, now I can do this using the product rule. So it's important to keep straight. If x is in the base, like in this first term, then we use the power rule. So the derivative of the first term is 2x. If the x is in the exponent, then it's an exponential function. And in that case, we have to use this rule that we just derived. So when we use the product rule to take the derivative of this thing, the derivative of the first function is 2x, and we multiply by 2 to the power x. And we have to add the derivative of the second function, which is log of 2 times 2 to the x. And then we multiply by the first function, which is x squared. So that would be the derivative of this function. Okay, let's look at another example. So let's suppose we want to find the linear approximation to the function f of x equals e to the negative x squared over 2 at x equals 1. So by the way, this function e to the next negative x squared over 2 is a really useful function. It's called a Gaussian function. And so knowing how to work with this can be useful in some areas of math. So let's see if we can approximate this by a line near x equals 1. So we have to first find the slope of the tangent line. So f prime of x will be equal to, by the chain rule, the derivative of this function in the exponent is negative 2x divided by 2. The 2's cancel, and we just get negative x. Then the derivative of e to the x is e to the x, so we get e to the negative x squared divided by 2. So that's our derivative by the chain rule. And this tells us that f prime of 1 is going to be equal to negative e to the negative 1/2. So that's the slope of our tangent line. So its equation is going to be y equals e to the negative 1/2 times x minus x0, which is 1, plus y0, which if we plug in 1 to this function, again gives us e to the negative 1/2. So we can factor out an e to the negative 1/2, and we get x minus 1 plus 1, or e to the negative 1/2 x. So that would be our linear approximation to this function at x equals 1. So in summary, we now know how to differentiate exponential functions using these two rules here. And so this increases the number of functions we can differentiate by a lot. We now can do power functions, exponential functions, and trig functions, and any combination of those through products, quotients, or function composition. So there's now a large number of functions we know how to differentiate easily without having to go back to using the definition of derivative like we did up here.